Greetings, fellow mathematicians. For our second problem, we're going to take a look at the Laplace transform of f of t equals t. Now, our previous first problem, we went through pretty much all the topics that you'll want to review. For this problem, we're ready to jump straight into it. So we're going to calculate the integral from 0 to infinity of now our function f of t is t, but our integral we evaluate is t times e to the negative st, where we integrate t from 0 to infinity. Now that you've gone through the first problem, knowing what to do, we're going to set this up as a limit, since we have an improper integral. We're going to have a limit as b approaches infinity, and then you replace the infinity with b. So our integral now goes from 0 to b of t times e to the negative st. All right, we know what to do from here. We're going to first evaluate the integral, and that's going to be where integration by parts comes in. So let's go ahead and do that. We have an integral from 0 to b. All right, we're going to choose u as t and dv as e to the negative st dt. So u will be t, dv would be e to the negative st dt. Calculate du and v. Du, that would be 1 dt, or just dt. And be careful when you integrate. You're going to get a factor of negative 1 over s times that exponential function. All right, now we can use our integration by parts formula, and keep in mind, we're going to use it where we have limits on the integral sign. So our uv term will be evaluated from a to b. So let's take a look at our uv term. Negative 1 over s times t times e to the negative st. And that is evaluated from t equals 0 to t equals b. This is your uv term. And then we subtract from that the integral of v du. Now keep in mind, your integration by parts formula, there's a minus in that formula, but notice your v du term, or the integral of v du, also has a negative. So a negative times a negative, I can write that as plus, and now our integral still goes from 0 to b for the integral of v du. So our integral here is from 0 to b of v du, 1 over s, times e to the negative st. All right, and notice this integral, thinking of s as a constant, it's pretty much the work that we just did here. The only thing we need to be aware of is properly evaluating this. Now I'm going to cut out some of the steps, but you can probably see why. Notice when I plug in t as 0, that factor of t, plug in 0, it's going to kill off that whole term. So when I evaluate this at 0, it just becomes 0. The only part that survives here is when I plug in t equals b. So that's the only surviving part. Negative 1 over s. T we're plugging in as b, so we get negative 1 over s b e to the negative sb. Subtract when you evaluate it at 0. That factor of t evaluates the whole term to 0. And now we can evaluate this integral. That integral comes out to, notice again, we get another factor of negative 1 over s. So we're going to get a negative 1 over s times 1 over s, 1 over s squared. And that's times e to the negative st. And we're going to evaluate that from 0 to b. All right, just be careful with your negatives here. Keep in mind there's a negative in front of this whole term. So when I subtract and plug in 0, there's going to be 2 negatives that cancel. Let's go ahead and write this out. I'm going to carry this term along. So negative 1 over SB e to the negative SB. We have a minus, and we're going to be subtracting after that. So let me put a set of brackets. Now we can plug in carelessly. Now let's plug in t as b. So we get 1 over s squared e to the negative sb, but now minus 1 over s squared, and we're plugging in t as 0. All right, and that does simplify nicely. Notice the negative times a negative distributing through the brackets cancel to a positive, and e to the 0 is again 1. So it looks like if we want to write this in a nice form before we evaluate the limit, a negative times a negative, that's going to give me a positive 1 over s squared. And again, the e to the 0 is just 1. And then we have minus 1 over s times b times e to the negative sb. And the first part in the brackets, we have minus 1 over s squared times the exponential function. And that is all the work for first evaluating the integral. Now we're ready to take the limit of that as b approaches positive infinity. So now we're on to step 2. We're going to complete it by taking a limit as b goes to infinity, and we're evaluating the limit of this expression, 1 over s squared minus 1 over s times b times e to the negative sb minus 1 over s squared e to the negative sb. All right, now we reviewed some basic limits in the first problem of this series on Laplace transforms. As b goes to infinity, this exponential term, that's a decreasing exponential, that goes to 0. Again, we are assuming s is positive, in which case if s is positive, that remains negative in the exponent. If s is negative, a negative times a negative becomes positive, and that's an increasing exponential. So, since s is assumed to be positive, this term does go to 0. That does not require L'Hopital's rule, but this part, with the factor of b times e to negative sb, this is going to require L'Hopital's rule. Now, you can kind of fudge it a little bit in differential equations, or there's some shorthand notation, but make sure you realize you technically need to use L'Hopital's rule for this. B is getting bigger towards infinity, the exponential terms getting smaller towards 0. Infinity times 0 is an indeterminate form, so make sure you go through the work on implementing L'Hopital's rule to show that that goes to 0. But notice the whole limit here is not 0. As b approaches infinity, the first part in the brackets, that has no b's in it. That's just going to remain constant, 1 over s squared. And that is our Laplace transform for f of t equals t. So like before, let's just write down what the transformation looks like. We started with f of t, or little f of t, as t. And by calculating the Laplace transform, all that work, we get 1 over s squared. So we might write that our Laplace transform, capital F of s, is 1 over s squared. And there we go. That's getting into some moderate work on using pretty much all the steps in calculating a Laplace transform, which is pretty much what your professor would expect in the beginning of your differential equations course on using the improper integral definition to calculate Laplace transforms. Now, really, where this is going is just establishing a bunch of basic transformation pairs, and very shortly, you're going to abandon using the improper integral definition and rely typically on a table of pre-calculated Laplace transforms. Hope you enjoyed the video. If you did, support the channel, like and subscribe.